All right. Hello, everyone. So, welcome to this session. So, this is going to be a problem solving session, and the agenda for today is going to be solving a few hard problems. And there will be two topics we'll be focusing on. So, the first topic is segment trees, and the second topic is around graph based problems, problems in which you haven't been explicitly given a graph, but you have to think about things and model some things related to your graph. And then you have to figure out what will be the nodes and what will be the edges and stuff like that, right? Okay. All right. So, yeah, so I think we can start now. Enough people have joined already. So, is my OneNote visible to you guys? Okay, okay. All right. Right. So, today we'll be solving two problems, and I've already shared the link to those problems in the Discord server. So, if you have already tried these problems, that is really great because if you were not able to solve them, you will be, I will let you know the solution and also the most optimized way to solve the problems, right? So, yeah, without any further ado, let's start solving with the first problem. I'll just share the link to the first problem in the chat box for those of you who haven't had the chance to read it. Okay, there you go. So, yeah, let's start. So, in this problem, basically, you are given n segments on a number line, and the ith segment covers all the points from Li to Ri, and it has a value of Wi. So, basically, we have n segments, n pairs of intervals, and every interval is defined by a starting point and an ending point, and it also has a cost associated with it. And we are asked to select a subset of these segments, possibly all of them. And once the subset is selected, what we'll do is it will be possible to travel between two integer points if there exists a selected segment that covers both of them. Right? I hope this makes sense. So if there are 2 points and all the points in between them are covered by the segments which have been chosen by us in the subset, in that case we can travel from the first point to the second point, right? Now, a subset is good if it's possible to reach point M starting from point 1 in arbitrary number of moves. Right? That is the problem. Okay. So the cost of a subset is the difference between the maximum and the minimum values of the segments in it. And we have to find the minimum cost of a good subset. Right? So a good subset is a subset in which we start from 1 and then we can reach the value M. Right? So that is the definition of a good subset. So in the input, we'll be provided with both N, M and all the intervals as well as their costs. So we have to find the minimum cost of a good subset. Okay. Yeah. So are there any doubts? Is the problem statement clear enough? If you have any doubts in understanding the problem, you can ask me. Otherwise, I'll give 5 to 7 minutes to you guys to actually think about the solution because this is a really good problem. All right. So if there are no doubts, I'll be giving you 5 minutes to think about the solution if you haven't already, and then we will start. Notice the definition of, notice the condition that is required to travel between 2 points. So we are allowed to travel between 2 points if there is a subset in our chosen segment, there is a segment in our chosen subset such that it covers both these points. So here in this example, if we label these 3 points as 1, 2, and 3, and if we have these two segments in the input, then we can confidently say that it is allowed to travel from point 1 to point 2 and then from point 2 to point 3. Why? Because the first segment covers both the points 1 and 2, and then the second segment covers both the points 2 and 3, right? Okay. So I hope now the problem is clear enough. So if you guys have any approaches, you are free to unmute yourself and tell me about it. Then we can. Yeah. So Satanshu, I will just repeat what the problem statement is saying. So basically, you have n segments, right? You have been provided with n segments starting from L and R. All the segments start from Li and end at Ri, and there is a cost associated with every segment. Now you choose a subset of these segments, right? And once you have chosen the subset, what happens is that you're allowed to move from one point to another point if there exists a segment in the chosen subset such that it covers both these points. And then if that is the case, then you can move from one point to the other point. And you have to choose the subset such that it is allowed to move from point 1 to point M, and you have to minimize this value, which is the difference between the maximum and the minimum cost of the segment present inside the subset. So you have to minimize the value W max minus W min of all the chosen segments in your subset, right? And here in this example, you can clearly see that we can travel from point 1 to point 2 because the first segment covers both these points. And then we can travel from point 2 to point 3 because the second segment covers both these points. All right. Yeah. So do you guys have anything in mind? I'll give 2 to 3 more minutes to think about it, and then we'll discuss the solution. Okay. Any approaches? It's okay even if you are wrong. I will highly encourage you to speak up. So this is the last minute, and then so Shubham says DP. Okay, so yeah, there is no DP here. That is for sure. We won't be using any kind of DP to solve this problem. All right, so let's start the solution with a very simple sub problem of this problem. So now we'll solve a very easier problem. So I'll give you guys a very, very easy problem. And using the solution of this problem, we'll build onto the solution of our original problem. So let's say we are given n numbers in an array. Okay. And we have to select a subset such that sum of chosen numbers is at least k. Okay. Now, among all the possible subsets whose sum is at least k, we have to minimize the same expression, max minus min. We have to minimize the max element minus min element among all the subsets that we choose. We have to choose just one subset, and it has to be such that this value, max element minus min element, is minimized, and the sum of the subset is at least k. So yeah, now can anyone tell me how we can solve this problem? We have to find the minimum value of max minus min. So this is a very easy problem. This is like a very basic problem, like 1200 or 1300 rated on Codeforces. And yeah, so can anybody pitch in and tell me how we can solve it? Yeah. So Sumit says for each maximum, we can find the greatest minimum. Now, how will you find the greatest minimum, Sumit? The approach is correct. Yeah. So Sumit says we can use binary search to find the greatest minimum. Okay. So is there any other method other than binary search from which we can find the greatest minimum if we fix the maximum? It is also another very well known method other than binary search, and it works in linear time as well. Any ideas? Yeah, so exactly. So we'll be using two pointers. So what we can do is either we can fix the maximum element and we can find the greatest minimum element, or what we can do is we can fix the minimum and then find the smallest maximum such that the sum becomes at least k. Right? And how can we do this? We can do this by first sorting the array. So once we sort the array and So once we sort the array and we fix the minimum, then we can just naively find out the maximum for a fixed value of minimum, right? So let's say we fix the min at I, and then we naively find the value, the maximum value, right? So then we naively find j such that sum from j to I exceeds k and j is as small as possible. Now, when we fix the minimum at I plus 1, then we don't need to iterate from I plus 2 to n. We can simply iterate from j plus 1 to n, and that is the basis of two pointers, right? So I hope I don't need to explain it much here. So yeah, this problem is basically solvable using two pointers. Now, yeah, I hope everyone has understood the solution to this simpler version of the problem. So are there any doubts in understanding this simpler solution? It's a very basic problem. You just have to find for a fixed minimum, you have to find out the maximum j such that the minimum j such that the sum from j to I exceeds k, and that can be done naively using two pointers. So are there any doubts here? I hope not. Okay, cool. Right. So yeah, so this is pretty easy, right? So if we observe here in this main problem that we still have a set of n elements. We have to choose a subset such that a particular condition is satisfied, and then we have to minimize the value of max minus min. Right. So here this condition was very easy to think about. The only difference in these two problems is the condition that needs to be satisfied. Right. So in the easier version, the only condition was that the sum of all the chosen elements should be at least k. So applying two pointers was easy for us, right? But this time the conditions are different. The conditions are that we have to choose a subset such that we can reach from point 1 to point m. So now let's try to find out a condition which is necessary and which makes sure that we can reach from point 1 to point m. So condition to reach from 1 to m. We can move between any two points if there is a single segment which covers both of these points. As you can see in this example, we can move from 1 to 2, and then we can also move from 2 to 3. So can anybody here tell me what is the condition that is required for us to reach from point 1 to point m? Anybody? Yeah, obviously you will have to sort the array first. All right. Can anybody tell me what is the condition from which is sufficient to say that I can move from point 1 to point m? It's also based on a very simple observation. It's not a very complicated thing that I'm asking here. You just have to observe what's going on in this picture, and then it will come to you naturally. So Mead says that the sum of points of all segments should be at least m. Yeah, so that basically won't work. And the reason is that there can be overlapping segments, right? So if there are overlapping segments, even though their sum of all the elements will be m, uh, we won't be able to reach from 1 to m. But yeah, if we say that, yeah, exactly. So Happy Potato says that if the segments cover all the elements, all the numbers from 1 to m, then we can reach from 1 to m. And that is pretty obvious. Here you can see that all the numbers 1, 2, and 3 are covered by some segment, and that allows us to move from one number to the other number. And that is pretty obvious because once we are at a point and we know that all the other points to the right of it are covered by some segment, it is pretty obvious that we can move from one point to any other point towards its right. So the condition is that all points from 1 to m should be covered by at least one segment in our chosen subset. Okay, so does anybody have any difficulties in understanding why this condition is true? So Sumit says, what about 1, 2, and 3, 4? Then can we move from 1 to m? Yeah, so we can move from 1 to m, right? So let me draw and explain it to you. So this is the first segment, and this is point 1, this is point 2. So basically, in this situation, what happens is that we can move from 1 to 2, but then we are stuck at 2, right? Okay, so this seems problematic to me. Let me draw it on a number line. So what this problem says is that the ith segment covers all integer points from Li to Ri and has a value of w. Oh yeah, yeah. So that's the problem. So what I mean to say is that if we are given a segment from Li to Ri, we will only consider it as a segment from Li to Ri minus 1. So if we have 1, 2, we will only consider it as 1, comma 1. And if we have 3, comma 4, we will only consider it as 3, comma 3. Why? Because I am converting the segments such that uh, in the range from L to R, every point in between is covered. So if we take 2 as well, then it will be a problem because this region from 2 to 3 will remain uncovered. Yeah, so this is a very valid question asked by Sumit. So what we'll do is, so if we have a segment of the form Li to Ri, we will only consider it as Li to Ri minus 1. The reason is that we are only looking at points such that everything in the region from I to I plus 1 is also covered. And that is true only for points from Li to Ri minus 1. That is not true from points for point Ri. Right? So we will convert Li comma Ri to Li comma Ri minus 1. And now this condition becomes true, that all points in 1 to m should be covered by at least one segment. Because if a point is covered, we know that the entire region from I to I plus 1 is covered by that segment. And if a new segment is starting from I plus 1, even then we can go from I to I plus 1. I hope this cleared your doubt, Sumit. Yeah, 4 is not included in this case, but then we will also decrement m, right? So yeah, that is another thing we have to take care of. We only need to make sure that we reach m minus 1. Why? Because once we reach m minus 1, we know that we have only taken points such that the entire region from I to I plus 1 is covered for every point. So once we reach m minus 1, we know for sure that the region from m minus 1 to m will be covered. So in that case, m will become 3 and then the answer will be yes. Any other doubts? So this is something that is worth writing. So we will make sure that if we have a segment from Li to Ri, then for any point, entire region, for any point I, the entire region, I to I plus 1 is covered. And that this is only true for points from Li to Ri minus 1. That is why I am decrementing Ri. And naturally, we will also have to decrement m by 1 because we only need to make sure that we reach m minus 1. Once we reach m minus 1, we have basically reached m because I and I plus 1 is covered always. This is a bit tricky to understand, but I hope things are clear here. All right. So if this is clear, now let's look at this condition. So all the points should be covered by at least one segment, right? So another way to write it is that if we maintain an array count where count of I is equal to the number of segments in the chosen subset which cover I. So if we maintain this count array, then count of I should be strictly greater than 0 for all I from 1 to m minus 1. Once this is true, we are sure that we can reach from 1 to m. I hope this is clear. Because every point should be covered by at least one segment. So count I should be at least 1 for all the numbers from 1 to m, from 1 to m minus 1. Yeah, so I hope this makes sense to everyone. All right, so let's forget about the segment tree and everything and let's try to naively implement this. So what we are going to do is we are going to apply 2 pointers, and instead of having this check that the sum should be greater than or equals to k, what we'll do is we'll see that the count array, every element in the count array is positive, right? And we can obviously very easily maintain the count array, right? So once a new element is getting added, we will just increment the count of all the elements in the interval. And when we are moving from I to I plus 1, we will decrement the count of all the elements which are in the ith interval, right? So what I'm going to say here is that we will apply 2 pointers. And the requirements that we need to satisfy is that when we add an element, when we add a segment, basically, we will increment the counts of all points in that segment. Obviously from Li to Ri minus 1. And when we remove an element, notice that in 2 pointers, once we go from I to I to I plus 1, we remove all the changes that have occurred due to I. So we have to remove all the points in the ith segment once we move from I to I plus 1. So when we remove a segment, we decrement the count of all points in that segment. Right. And the check that we need to satisfy is that count of I should be greater than 0 for all I. And another way to write this is that the minimum element of count of I should be greater than 0. If that is the case, then obviously all the elements of count of I should be greater than 0. So minimum count of I should be greater than 0, right? Now, if we naively implement this, obviously this will tail because this is a lot of work. So adding an element will mean we are incrementing everything in Li to Ri minus 1. And as you can see in the problem, Li and Ri can be very large. They can be from 1 to m. And similarly, we have to check for all the elements of count from 1 to m that their count should be positive, and that is again a very costly process. So yeah, these are the three requirements that we have. We have to increment the count of a range, we have to decrement the count of a range, and we have to find the minimum element of a range. Yeah, so how do we sort the intervals? Again, that is a very interesting problem. So we notice that we have to minimize maximum minus minimum. So how will we sort our segments? Can anybody tell me? Yeah, of course. So we are going to sort the segments based on their W values, because the value which we have to minimize is W max minus W min. In the easier version, we just have to minimize we just had to minimize the maximum minus minimum of all the array elements. But here we have to minimize W max minus W min. So obviously we are going to sort the elements based on their W values, right? Cool. So now can anybody tell me a data structure which will help us carry out all these three functions, and that too efficiently? Although I have already told you. Great, great. So Sumit says that this can be done by using lazy propagation segment tree. Awesome. So what we can do is we can have a segment tree which does range updates for us, and it also does point queries for us. So what we have to do is we have to add something in a range. That is a range update. We have to decrement something in a range. That is another range update. And we have to find the minimum element of a range. So minimum of count of I for all I from 1 to m. 1 to m is also a range, right? So we have to find the minimum in a range, updates in a range. And a data structure which does all of this is segment tree. So segment tree with lazy propagation can handle all the three requirements for us. Cool. So the problem is basically solved now. So what we'll do is we'll maintain a segment tree. Instead of maintaining this count array, we will maintain the counts in a segment tree. And once in two pointers, we are expanding our range. What we'll do is we will do some range updates and increment all the values in the segment. Once we are reducing our range, we are moving from I to I plus 1. So we will decrement some elements in a range. That is another range update. And once we are done with all of that, we will just find the minimum element using the query of the segment tree function. And that's it. That is basically it. That is the entire solution. So notice how we started from a very easy problem, and 99% of the solution is just the same. And we just have this segment tree extra with us, and just this one observation that every point from 1 to m should be covered. And we have solved a very hard problem. This is a 2100 rated problem. And I think uh, solving all the problems starting from some very easy sub problem is a very nice way of approaching problems like this, right? So yeah, this is the entire solution. And now I'll be taking some doubts. So if you guys have any kinds of doubts in understanding the solution, I think there should be some doubt related to why we are decrementing Ri, why we are decrementing M. So if there are doubts like that, you are free to ask now. But how do we remove the overlapping unnecessary segment weights? Yeah. So the thing is, we don't have to worry about that. Why? Because if count of I is greater than 0, then that means at least one segment covers it. And all we are interested in is knowing that there should be at least one segment which covers all the points. So we just have to check if count of I is greater than 0 or not. And that can be done very beautifully using the minimum query of a segment tree. So we will just find the minimum element. So if the minimum element is greater than 0, we don't care about what is intersecting and what is not intersecting. Yeah, so I will be going through the implementation as well. But although I won't be implementing a segment tree from scratch, obviously, I have a code and I will just show you guys the code and go over the code. Yeah, so Siddharth, is your doubt clear now? How? Yeah, so I hope it's clear. Cool, cool, cool. So, any other doubts? All right. So, if there are no doubts, I'll just quickly go over the solution again, and then I'll show you guys the code. So, the basic solution goes like this. First thing is we sort the elements based on their value. And once we have done that, what we do is we apply 2 pointers, and in 2 pointers we basically fix the minimum element, and then we try to find out the smallest value of the maximum element. That way, for every minimum element, we'll have the minimum value of the expression max minus min. And to do that, we have a few requirements. One requirement is that we have to have a data structure which increments in a range, which decrements in a range, and which tries to find out the minimum element in the range. And a segment tree can do all of these things. And we have reached to this conclusion because we made the observation that every point should be covered by at least one segment. If we only look at if we decrease ri by 1 for every I, and we also decrease m by 1, then we only have to make sure that every point is covered by at least one segment. And using that observation, we found out all these three conditions, and then we realized that a segment tree with lazy propagation can easily solve our problem. So yeah, this basically completes the solution. Okay, so if you still didn't understand how we are removing overlapping segment weights, I'll just go over it again. So basically, it doesn't matter if things are overlapping or not. If you look at this condition, the condition is that every point should be covered by at least one segment. That is the condition, right? And if every point is covered by at least one segment, if we maintain an array count of I, where count of I denotes the total number of segments which cover this point, then the only requirement that we have is that count of I should be greater than 0, right? No other requirement. And using our segment tree, we are actually maintaining all these counts. So we just have to find out the minimum element. And if the minimum element is greater than 0, we know that every segment is covered by at least one segment because count of I is greater than 0 for every segment. And that makes sure that every point is covered. So yeah, now let's just quickly have a look at the code. So here is my code. So the segment tree is basically a very simple segment tree. I haven't used some fancy structures and things like that, just so you guys can understand better. So I just have a very basic implementation of a segment tree, and we are using a tree array and a lazy array, where lazy of I denotes the lazy value of the current node. And this is pretty basic. We are building the segment tree, and this is the range function. First of all, we propagate our lazy, and then we apply the common range function of a segment tree, and we do the similar thing with the update function. So yeah, this is like a very common segment tree with lazy propagation. So if you don't yet have a template, I think this is a good enough template for you to copy. So you can copy this and use it as well for other problems, right? So yeah, this completes the segment tree. Now let's see. So we have an L array and an R array, and we also have W. So we are taking in Li and Ri, and we are storing W in pairs. So Wi dot first is the value, and Wi dot second is the index. So using this index, we can access Li and Ri. That is why I'm having this index as well. So then what we do is we sort all the values based on their W, right? And then I build my segment tree from 1 to m minus 1, because we only need to make sure that we start from n and we reach m minus, we start from 1 and we reach m minus 1, right? So now I apply 2 pointers. Initially j is equal to 0, right? Now I go from 1 to n. I denotes the starting point of my interval, that is the minimum element which I'm fixing. And then I try to find out the minimum element in the range from 1 to m minus 1. That is the minimum count of all the numbers from 1 to m minus 1. So while this minimum element is still less than or equal to 0, that means while not all the points are covered and j is less than n. So this is pretty basic 2 pointers. So we have to use this j less than n condition. And this is the basic condition of our problem, that minimum element should be at least 1. So we increment j, and then we update the value of the segment lj to rj, right? So not j, wj dot second, because that is the index, right? So then we update these values and we update them by 1. Why? Because there is one segment, that is the jth segment, which is affecting all the points from L to R. So we take this range and we add 1 to this entire range. Notice I have this -1 here. That means I am decrementing R by 1. And then I update my minimum with the minimum element in the range, right? And finally, if the minimum element is greater than 0, that means if my condition is satisfied and j has not yet reached n, then I will update my answer with max, which is wj dot first, minus min, which is wi dot first. And once I'm done with that, don't forget that I also have to now move from I to I plus 1. So I have to remove the segment I. For that, I will update wi dot second of L and wi dot second of R. And then the update would be -1, because this time I will be decrementing everything by -1. And the ith segment is getting removed. And finally, we output our answer. So yeah, this is the entire solution. Okay, so are there any doubts in the implementation part? Yeah, so it's a bit tricky to understand, so I'm going to explain again. Why are we decrementing Ri? So notice that I have to maintain this invariant. So if we are having a segment Li to Ri, then we will make sure that the entire region from I to I plus 1 is covered. So if we have a segment from Li to Ri, let's say we have this segment. These are the points. This is Li and this is Ri. So for all the points in Li to Ri minus 1, in all these 3 points, everything from I to I plus 1 is covered, right? Everything from I to I plus 1 is covered, but that is not true for this point. That is not true for Ri. And that is the reason we are not including Ri to the answer, because if we do that, if we include Ri to the answer, then we will have situations like this. We will get situations like this. Here, you can see that every point is covered, but still it is not possible to reach from 1 to m, because once we reach from 1 to 2, we will be stuck here because we can't go anywhere to the right. So if we decrement Ri by 1, we are making sure that such situations never arise. So does it make a bit of sense now, Shubham? Cool, cool, cool. All right. So I think we are done with the first problem for the day. I hope you guys found it interesting enough. Right. So now let's go to the second problem. So this was a 2100 rated problem, and the second problem is going to be 2200. But I think it's going to take some less time because it doesn't have a very involved solution, right? All right. So yeah, if there are no more doubts, I think we can start with the second problem. I'll just share the link in the chat box. Okay. So so now Lenny had an n cross m matrix of positive integers. And he loved the matrix so much because each row of the matrix was sorted in non-decreasing order. So we have a matrix in which each row is sorted in non-decreasing order. And for this reason, he calls the matrices of integers lovely. Now, one day when Lenny was at school, just a minute. So one day when Lenny was at school, his little brother was playing with Lenny's matrix in his room, and he erased some of its entries and changed the order of some of its columns. So some of the entries have been changed, some of the entries have been erased, and some of the columns have been interchanged, right? Erased some of the entries of the matrix and changed the order of some of the columns. So he permuted the columns, right? So when Lenny got back home, he was very upset. Now he wants to recover his matrix, obviously. So help him find an order for the columns of the matrix so that it's possible to fill in the erased entries of the matrix to achieve a lovely matrix again. And we are allowed to fill the erased entries by any integers that we want, right? So the problem says we have to find an ordering of the columns of the matrix such that if the columns are ordered in this way, then it's possible to replace all the minus ones with some values such that after we have done all the replacements, the condition for all the rows being sorted in non-decreasing order is satisfied. Right? So this is the problem. So does anybody have any doubts in understanding the problem? If that is the case, you are free to ask. Otherwise, I'll again be giving you 5 to 7 minutes to think about the solution. So if you have anything in mind, any approaches, I will encourage you to unmute yourself and even speak. And if that is not the case, then you are free to write in the chat box as always. Okay, so any approaches? So I'll tell you guys beforehand that this problem is related to graph. So try to think about what are the things that you can represent as nodes in the graph and what are the things that you can represent as edges in the graph. I think it is pretty obvious what you have to represent as nodes in the graph. So yeah, can anybody tell me what should be the nodes in our graph? Awesome, awesome, awesome. So Sumit says that we will have all the columns in the graph as nodes in a graph. And when we have a relation that the ith column should appear before the jth column, we add a directed edge from I to j, and then we perform topological sorting. And that is exactly what we are going to do here. Although not in a very straightforward way because the number of edges might be very large, but that is the basic idea of the solution. So I'll give 2 more minutes for everyone to think about the solution and then we will be starting. Meanwhile, if anybody else thinks about a different solution or the same solution, you are free to discuss. Okay, all right. I think I have given enough time. So now let's start with the solution to the second problem. So to describe the problem, we have a matrix with some unknown values. Some of the values are minus ones, and we have to find an order in which we can permute the columns matrix such that after permuting what we have to make sure is that the previous relations, according to the problem, you can easily see that what we have to do is we have to find an order of the columns for the matrix so that it is possible to fill in the erased entries of the matrix to achieve a lovely matrix again. And what was a lovely matrix? It was a matrix such that for each row of the matrix, we have the relation that every element in every column is sorted in non-decreasing order. So, so after permuting, it is possible to replace each minus one with any number such that every row is sorted in non-decreasing order. So this is the basic problem. Now let's go over the solution. Yeah. So the basic idea of our solution is that we will try to build a graph, right? So the nodes in the graph are going to be nothing but the columns. And that is a pretty obvious observation because we have to find an ordering of the columns and we have some relations that a particular column has to be before a particular column. And so it basically gives us an intuition that we have to have some relations and some nodes. So that means we can model this problem as a graph. So the nodes in the graph are going to be the columns and edges are going to be relations from, so we have an edge from I to j such that it is necessary to keep column j before column I. And when will be the case when we are keeping column j before column I? So can anybody tell me when is it necessary that the ith column should appear before the jth column in the final permutation? When will that happen? If there is an inversion between the ith and the jth column, ignoring minus one. Yeah, so I mean not inversion, but the reverse of inversion, right? As you can see here, if we look at the first test case, in the second row, we can see that in column 1 we have a 1 and in column 2 we have a 2. So obviously the first column has to appear before the second column, right? Because if in our permutation the first column appears after the second column, then we will have a 2 and then a 1, which is not allowed because this won't remain in non-decreasing order, right? So basically, in any row, if in any row R, we have two columns I and j such that ARI is smaller than ARJ, then ith column has to occur before jth column, right? Because now if the ith column comes after the jth column, then this particular row will no longer remain sorted in non-decreasing order. So it can remain sorted if and only if the ith column appears before the jth column, right? Okay. Now, another observation is that once all these conditions are satisfied, so once we have a permutation which makes sure that for every row R and for every pair of columns I and j, if ARI is less than ARJ, then the ith column appears before the jth column. then we have a good matrix, and then the matrix is valid. The reason for that is that we have to choose what we can replace the minus ones with, and it is always possible to find some random numbers such that we can replace the minus ones with those numbers and every row remains sorted, right? So the observation that I'm trying to make here is that once all such conditions are satisfied, what we will get is we will get a matrix whose every row is sorted if we ignore the minus ones, right? Now, if we have a sorted sequence and some minus ones inserted randomly in that sequence, then we can always find some suitable values for the minus ones such that the sequence is still sorted, right? So that proves that once all the conditions like this are satisfied, so once all such conditions are satisfied, then we will have a valid matrix because it is our choice. We are allowed to fill the minus ones with any number that we want, right? Cool. So does anybody have any doubts in understanding what's going on till now? Even if everything is clear, I would recommend you to just write it down that everything is clear so that I get to know that people are following. Cool, cool, cool. So Shubham says that if there is a cycle, it will be minus one. Obviously, that is again a very great observation. So if there is a cycle in this graph, so let's say we have these nodes and we have an edge from this node to this node. That means, so let's say this is column 1, this is column 2, this is column 3. So this edge, this first edge says that column 1 should appear before column 2. And this edge says that column 2 should appear before column 3. And this edge says that column 1 should appear before column 3. Now, obviously, if column 2 is appearing to the right of 1 and column 3 is appearing to the right of 2, then 3 is appearing to the right of 1. And then this third edge becomes impossible. It is not possible that 3 appears to the left of 1 because according to these first two edges, 3 has to appear to the right of 1. Cool. So I was coming to it, but yeah. Awesome. Awesome. Now, can anybody tell me once we build the graph, just forget about how we are going to reduce the number of edges and what we are going to do after that. Just tell me once we have built the graph completely and we have the graph with us, can anybody tell me how we can find this valid ordering of columns? That is a valid ordering of nodes in the graph such that all the conditions are satisfied. Although Sumit has already told the solution, can anybody tell me what we have to do here to find the valid ordering of the columns? Yeah, so that is the very definition of topological sorting. So I hope you guys remember when you study about topological sorting, you are given a problem where there are some courses which are represented as nodes in the graph, and the edges in the graph are basically relations like one course is a prerequisite of the other course. So if course A is a prerequisite of course B, then there is a directed edge from A to B, right? And we have to find out an ordering in which we can do the courses such that there will be no situations where we are doing a course whose prerequisite hasn't already been done, right? So that means if we have an ordered edge from A to B, then in our ordering A has to appear before B. And if you notice, this is exactly the same situation here. We have a graph and the relations denote that the first node in the edge should appear before the second node in the edge. So we can simply apply a topological sort, right? So yeah, so I hope it is clear. We will apply topological sort to the graph. So the problem is solved, right? It looks so in the first look, but that is not the case because the number of edges in the graph can be very huge. And the reason for that is that we can have an edge between every pair, right? So for in any row, so if you look at the constraints of the problem, the total number of elements that we have is 10 raised to the power 5. So let's say we just have one row, and in the one row we have 10 raised to the power 5 elements. So what we are doing is we are looking at all the pairs of columns in the row, and we are checking if a1i is less than a1j. And let's say that this thing is true for all the pairs I comma j. So this will be true when the entire row is sorted. So let's say that the entire row is sorted already. So in that case, if we go over all the pairs, then we will have O of n square edges, right? O of m square edges. If n is equal to 1, then we will have O of m square edges, and that can be very large, right? So we can't simply just naively build a graph. So can anybody tell me something which we can do to optimize this process such that the number of edges in the graph is reduced? So that is again not something very out of the world and not something out of the box. This is something that is pretty common. Awesome, awesome. So others says that we only have to check adjacent columns. Now, why is that the case? So let me see. Let's say we have three numbers in a row, 1, 2, and 3. So what we were doing previously was we were looking at 1 comma 2 and we were saying that the condition is satisfied. So we add a directed edge from 1 to 2. And then we do the same thing from 1 to 3, right? And now we look at 2 comma 3 and then we add the same edge from 2 to 3, right? So notice that this third edge here is simply redundant because if 2 is to the right of 1 and 3 is to the right of 2, then obviously 3 will be to the right of 1. So that means that this third edge is basically redundant. So we can just remove this edge. So now what happens is that we only need to check adjacent columns. Okay, now is the problem solved? Well, not really. The thing is that this is a 2200 rated problem and the solution can't be that obvious, right? Now, can anybody tell me the problem in this version? Will this always guarantee that the number of edges that we have is small enough? Do you think that this will guarantee? Awesome, awesome. So Happy Potato has mentioned a case where the number of edges will still be very large. So what if the row that we have looks something like this? 1, 1, 1, 1, 1, 2, 2, 2, 2, 2. Here, what are you going to do? So basically for every pair of 1 comma 2, you don't have any choice. You have to add an edge, right? So for every 1 and 2, we have to add an edge. Because if we simply choose a particular one and choose a particular two and add an edge between them, then what about the remaining ones and the remaining twos, right? What happens to them? So in that case, let's say we have 10 raised to the power 5 numbers and the first half of them are ones and the second half of them are twos. So in that case, we'll have 10 raised to the power 5 square, O of 10 raised to the power 5 square edges, right? And that is again very large because we have to have an edge between every one and every two. Is this clear why this approach will not work in a straightforward manner if we simply check adjacent numbers, adjacent columns? So if it is clear, I encourage you to use the chat box and just write that it is clear. That gives me confidence as well. And if it is not clear, then you should ask what are the things that are troubling you. Okay, so it is well established that this method is not going to work in a straightforward manner. Now, can anybody tell me how we can optimize this and how we can actually reduce the number of edges such that the number of edges is O of nm? Nm is up to 10 to the 5, so I want to have the number of edges around n into m. Can anybody tell me how we can do that? Yeah, yeah. So the last part is that what we were doing was we were looking at all the pairs of columns, right? In a particular row, we were looking at every pair I comma j of columns, and we were checking if ARI is less than ARJ. And if that is the case, we were adding an edge between the ith column and the jth column, right? But in the worst case, what could happen is that we could have just one row, and there can be 10 raised to the power 5 numbers in that row, and then that sequence might be sorted. And in that case, ARI is less than ARJ would be satisfied for every I less than j. And so we will end up with O of m square edges. And you can see that that value is up to 10 to the 5. So m square will be very large. And so the number of edges will be very huge. So to tackle that problem, what we did was we just checked adjacent nodes. We just checked adjacent columns. Why? Because as you can see in this example, if we check 1 to 2 and 2 to 3, then we also had to add an edge between 1 to 3, but that was redundant because if 1 is to the left of 2 and 2 is to the left of 3, then automatically 1 becomes to the left of 3. So we don't have to explicitly add an edge from 1 to 3. So what we did was we only added edge from adjacent columns. We only checked adjacent columns, and that looked fine, but that could have been fine if we were not allowed to have duplicates. But here we could have duplicates as well, so we could have a situation where half of the elements are 2 and the other half of the elements are 1 and the other half is 2. In that case, we have to add an edge between every 1 to every 2, and that will again lead to O of m square edges, right? So now I'm asking you, is there any way you can still reduce the total number of edges? Any ideas? So that is the most tricky part of this problem, how to actually reduce the number of edges. There are some high rated people as well in this chat. So, uh, yeah, so I would like to ask you, do you have any ideas how to decrease the number of edges? I'll give another minute and then I will discuss the solution. Try to think on the lines that we can group all these ones together and we can group all these twos together. So try to think what we can do if we group all of them together. So I'll give you another hint. So consider an algorithm for finding multi-source shortest path in a graph, or maybe just consider multi-source BFS of a graph. So what we do there is we introduce another dummy node in the graph, and we add edges between all the sources to that dummy node. Right? That is the first step that we do. So try to think on that lines. All right, so I think it's time to tell you guys the solution, and the solution is actually pretty simple. So what we'll do here is, so we have all these ones here, right? And then we have all these twos here. Our main goal is to have some edges such that if we translate all those edges in English, the situation reads that everyone should be before every two, right? We need to make the situation such that everyone should appear before every two. and the edges should be such that the first end of the edge should be to the left of the second end of the edge, and we have to add a small number of edges. So what we'll do is we will introduce a dummy node here. So let's say we introduce a dummy node here, and what we do is from each one we add directed edge to the dummy node. Similarly, for each two we add directed edge from dummy node to itself. So for each one, what we'll do is, so for each of these ones, we will add directed edges here. So on and so forth. Similarly, for each two, we will, so the direction of these edges is like this. And for each two, we will add a directed edge from the dummy node to that two. Something like this. So we will do this for all the ones and for all the twos. So you can see that this makes sure that every one is to the left of every two. And that is basically what we wanted. And the total number of edges here will not exceed 2 times nm, because for every one we are adding one edge, and for every two we are adding, so for every one we are basically adding one edge to the right, and there can be some dummy node here to which we are adding edges like this. So for every element we are adding exactly two edges, so at max two edges, right? So the number of edges will not exceed 2 into n into m, and nm is 10 to the 5, so 2 into nm edges are just fine for us, and that will do our job. So now we have a graph with a limited number of edges that we can deal with, and we just have to find a valid topological sorting of that graph. If the topological sorting doesn't exist, then the graph will be cyclic and the answer will be -1. Otherwise, we just have to output the topological sorting, and we don't have to take into account the dummy nodes in the topological sorting. So once we have our topo sort, we will just remove the dummy nodes from them and output the rest of the nodes in the same order, right? So is this thing clear? Is it clear how I am adding a dummy node and how adding a dummy node makes sure that all the conditions remain same and the number of edges are magically reduced? Yeah, so the number of dummies that we need will be around the total number of distinct elements in the graph, right? And the distinct elements again can't exceed nm. So yeah, the number of nodes are also getting increased. So the number of edges are getting decreased on the cost of the number of nodes. So nodes are getting increased and edges are getting decreased. Yeah, so for each column, we can have one dummy node, obviously. If all the elements, if in a row, all the columns are distinct, all the columns are unique, then we will have one dummy node for each column. And that is still okay. We'll have at max 2 nm nodes and at max 2 nm edges. Cool, cool. So yeah, this is the entire solution. So if you have any other doubts, this is the time to ask. Otherwise, I'll just show you guys the code. I had another idea. if what if I sort on the order of columns using a custom comparator? What exactly are you doing? So there are n rows, right? You have to take into account every row, and you have to find an ordering such that every row becomes sorted, right? So you can do that for one row, but there are a lot of rows, right? And you have to make sure that it is sorted for each and every row. So I don't think you can just simply use a comparator and sort it out. Okay, so what you're doing here is that, yeah, so you are basically simply ignoring -1s and sorting, right? So that will give you different ordering for different rows. So what will you do of that? You have to have just one ordering. and that should satisfy the conditions for all the other rows.
No, no, I am sorting the entire column actually. So like for each pair of columns, I am checking the comparator using the all the rows.
Okay.
So here X and Y are the ID of the column.
Yeah, so X and Y are the ID of the column and I is the row, right?
Yes, yes.
So in this case, there can be many relations, right? Sometimes it should happen that AIX is greater than AIY. Sometimes it will happen that AIX is smaller than AIY. So what exactly are you doing there?
So like if we find any, like if there is an element in any row
Yeah.
such that it is greater than the element in the other column, so like we have to swap that column definitely. So there I return false.
So you are not building any kind of graph, right?
No, no.
So I don't get why this will satisfy the condition for every row. So have you used this and submitted your code using this?
Yes, yes, but it's not working.
Yeah. So that's an issue. This is not going to satisfy for all rows, right? Cool. So 1 2 2 1, this fails. Yeah, obviously this will result in a cyclic graph, right?
But after sorting, I'm just checking if it is possible, like if the ordering is correct or not.
Yeah, so this won't, like, this might produce a good result, but this doesn't guarantee that it will always produce a good result, right?
Correct, correct.
Okay, any other doubts, or should I just show you guys the code now? The code is pretty simple. All right. So yeah, let's just go to the implementation once. Cool. So what we are doing here is that we are maintaining an adjacency list and we have some nodes. Right now, the number of nodes in my graph is m because we have m columns. And as soon as we discover new elements, we will keep introducing new dummy nodes. So what we do is we take in the input row by row. So now once we are taking all the elements in the ith row, what we do is we sort all of them, and we also keep in account the column that they were initially, and that is why we are taking the entire row into a vector of pairs. So the first element is the value and the second element is the column number. So once we have sorted it, what we do is we pair up all the adjacent pair of equal numbers together. Obviously, we will be ignoring minus ones. And then what we do in this loop is we try to figure out that starting from the index j till where are we finding the same elements, right? So obviously, once we have sorted, the same elements will be grouped together. So for all the elements from j to k minus 1, they will have the same value, right? Cool. And then what we do is once we have all of these vectors together, what I'm doing is I'm incrementing n, that is I'm introducing a dummy node, and then in the particular vector I am adding an edge from x to the dummy node. So these are edges like this. So from 1 to the dummy node. And then what I'm doing is I'm using the dummy node and then I'm adding an edge from the dummy node to x. So these are edges like this from dummy node to 2. So I'm doing this for all the unique elements in my row, and I'm doing this for each and every row as well. So now I have done everything. So I will have a graph which is very well valid, which has my nodes as columns and which also has some extra dummy nodes. And then I'm just using the conventional algorithm of finding the topological sorting of a graph by using the in degrees and using a queue. This might also be known as the Kunz algorithm. I am not really sure. So yeah, we basically find the topological sorting by using the degrees. So we keep popping out elements from the queue, and then we decrease the degrees of all the adjacent elements. And as soon as the degree of a number becomes 0, we push it into the queue. And if the graph is cyclic, then the size of the topological sort won't be equal to the number of nodes in the graph, in which case the graph is cyclic. So we return -1. Otherwise, we look at the topological order. We remove all the nodes which are greater than m because those are dummy nodes. Once we have the nodes from 1 to m, we know that they are the columns and all the other nodes are our dummy nodes. So we will ignore all the dummy nodes and then we will print out all the other nodes which are our columns. So then we will have a valid ordering of all the columns such that everything is satisfied. I will just again explain how I am building a graph. So in the graph, what I am doing is I am having a vector of for every row. What I am doing is I am having a vector of vector. So basically, let's say we have a situation like this: 1, 1, 1, 1, 1, 2, 2, 2, 2, 2. So this vector of vector will contain two vectors. First of them will contain all the ones, and second of them will contain all the twos. And then I will add an edge from all the ones to the dummy node, and I will add an edge from the dummy node to all the twos. As you can see, from vec of j, I am adding edges to the dummy node, and from the dummy node, I am adding edges to vec of j plus 1. Cool. So this is how I'm building my graph, and this is how this works, and this pretty much completes the solution as well. Yeah, so this completes both the problems that we had today. So if there are any other doubts related to these problems or even unrelated, you can ask me right now. Otherwise, we are going to end the session. So if you understood the solution, I would encourage you to just write a yes in the chat box. Cool, cool. So if there are no other doubts, I think we can end the session now. Yeah, so this dummy node technique is used in a lot of problems. And a very good example is the one that I just gave you. In multi-source BFS, what you generally do is you just add all the sources into our queue. But behind the scenes, what you are doing essentially is you are introducing a dummy node and you are adding an edge from the dummy node to all the elements in your sources vector. And then you carry out a BFS from the new dummy node that you added. So that is a very good example of this dummy node technique. But yeah, in general, adding dummy nodes is not very uncommon in graph problems. Cool. So thank you so much everyone for joining. And I will see you guys in the next session, which will be held sometime later because right now I am a little bit busy. So the frequency has reduced, but I'll make sure that I try to have more and more of such sessions as soon as possible. Right. So yeah, see you guys later. Bye bye. Thanks for joining.